Hello, everyone. Just give me a moment to share my screen, then we can start accordingly. Okay, just one moment. Okay. All right. I hope my slides are visible and we should be able to start. So let's begin. Okay. So this work is mainly concerning about an electronic health record system for real-time prioritization of patients. So this is something that I had worked on when I was currently doing my undergrad at the time, and I kind of developed it over time with multimodality. So let's dive into it. So I think a lot of us are familiar with the fact that, like these developing countries or countries that are being currently developed, electronic health record system is like a lot backdated for a lot of reasons. There's not that amount of funding. One of the main milestonical issue is the inefficiency, limited time, no concrete decision support, high amount of patient volumes, and especially like in alarming rates of diseases where the triggering delays are very high and there's a high amount of overload of data, especially from health organizations, especially like hospitals. And when you have severity of patients, which can, be, I guess, in some form categorized based on what level of priority they require. So this is kind of where this idea and this motivation stems from, that for critical patients where there is a high amount of approximation of delays, is there a way to maybe give increased throughput to clinicians in terms of workloads, reduce maybe the operational efficiency in online or on the internet, or is there a way to make the management much more easier? So, like in the US and UK, electronic health records have been significantly developed over the years. And in terms of like traditional paper records with thousands and thousands of papers, electronic health record has given a lot amount of accumulation in terms of innovation and accessibility and also organization management. So the context basically stems from this idea, but initially when this prototype was trying to be implemented in phase. This was more, I guess you could say, hard coded in a lot of sense because this was developed under the Visual Studio environment. And the idea was that can a system software be created and be further tested in certain hospital based on their records and the patient entry? Because, this is about health. So this was like a tested prototype that I initially wanted to like implement in my own country. And like there's a lot more people who are not into the idea like, why do we need this system or what is the main requirement? So it was like a mixed approach in a lot of sense. Some people were on board with the idea, some people didn't understand it, especially for like rural, urban areas. People were like, what is this basically going to help with? So to come to the main objectives of this work, which is now have been integrated with AI, with multimodality and generative artificial intelligence, or more in state of the art, as we call it, agentic AI. So the main contribution concerning this work is like the transparency for the prioritization mechanism. I'll give you more details as we move along the presentation. So this integrated EHR architecture is like a pipeline for like next generation, or maybe you could say like state of the art medical system online for developing countries. And it can be utilized based on what type of queue and what type of data that you basically have. And we did an experimental validation using some workflow improvements. I will show you more on that as we move along. So coming to the main system overview, like how this thing basically came about. So this has different layers encoded to it. There's a software part, there's an encoding part, there's a database part, then there is the data itself, then it's the patient records, and then you have the integration of the doctors, their availability, their profiles. It's a very big architecture, but I'll try to give it more concise in terms of the infrastructure usage and like how this was like brought about. So coming to the data, which is like the main part, because this is where we need to do the pre-processing, post-processing. So we use the K9 data analytics to like make the decision support modules, which was later integrated with generative models to see how the application interface can be maneuvered and probably be automated in a lot of sense. So the main hard-end backcoding was developed in C Sharp, which was then moved to Python because now almost everything is Web3 based. So, and the SQL Server is basically the database. Now, this can be integrated based on how many hospitals or how many data records you want to invest or put in. So it basically depends on the platform or the organization that wants to utilize this kind of architecture. And considering the system functionality where the main attribute, which is like the patient record and how the priority queue can serve as like an automated queue for real-time assimilation. Now, you might be asking like, what do I mean by this vital analysis of queue prioritization? Okay, so I'll give you an example. Let's say you have multiple patients, right? And by the way, this can be done online. You can pre-book, you can use your phone, you can use a software application directly from your Android or your iOS. So the main idea is that let's say you have a patient who has fever, like normal running fever, a patient who just had an accident, probably a broken limb or probably a very high issue. And then from the other end, you have someone who's just been like having a severe stroke. So you have different categories of patients, right? So the priority queue is based on that particular, I guess you could say, support module. The architecture is designed on that sense. Initially, what I did was that, okay, I give priority one, priority two, priority three for every single patient when they're including their entry. Because, like, for instance, the person who needs surgery immediately is obviously priority one. And then a person who may have fever, but it is not that much elongated. So he can be put in the stack of the queue, maybe priority three, priority four. Let's say someone just had a stroke, so they need to be put into the ICU immediately. So this is how the prioritization basically came into fruition. And then later on, this development was kind of embedded with multimodality. Now, this also depends on the type of data the hospital is going to be utilizing in terms of this architecture. Because like the more data you put in, the more information the model has, the better it will be able to fine tune and automate the entire system based on that architecture. And especially like in developing countries, like for my country or like other countries who are trying to utilize this system, this can be like a pathway for them to like move towards. Now, this is kind of like the overall experimental workflow, which we basically use because the software is kind of integrated in different UIs, basically. You have one for the patients, you have one for the medical personnel, then you have the doctors, and then you have the priority stack, which handles all these records, whether it is from the hospital, whether it's the doctor's data, patient data, and then you have like an interface record which is being done for the processing integration, and you have the AI brain, which is basically a model at this point. It goes through all the analytics of the data that's been fed to it, and it creates the terminological service, and based on that it creates the system management and runs everything from that automation, basically. So it's still being a work development in process because, as I mentioned, this is more data driven. So it depends on the amount of data or the type of data you integrate in this service or architecture. Now, the experimental evaluation, if you come to it, we had done previous records, some state of the art, and then we tried to test this in some hospitals. Like I mentioned initially, like in my country, I tried to deploy this, and initially, like when I went to certain hospitals, they were not into the idea. They didn't want to apply this kind of workflow because they needed to give me information data from their hospital. They didn't want me to connect my software to that particular platform. But also there were a lot of hospitals who were like very interested, and then they said, yes, we're interested in to see if this system can help us maybe leeway the management system or probably make things a little more automated so that physicians, doctors, patients have more room for controlling. Because like in my country, I'll give you an example. In our country, where it's very chaotic when it comes to like, assembling patients in terms of like even just for finding a space or like trying to find a doctor or like trying to find a physician to see or sort out your problems, which is like a very big hassling thing, which is even still ongoing today. So this is where like this idea mainly stemmed from. And then from the evaluation point of the AI model, what it basically can do is like, that with agentic AI, we can do predictive analytics in a lot of sense. So if, let's say, you have an entire infrastructure system data from a patient's personal records, what type of diseases they had, what type of issues that they were facing, and what type of medical information and what type of disease they currently have in their anatomy. If all these things are integrated in the record storage, which is basically the patient information, and then all the accumulations of all the medications that person has achieved, whether he or she has gone through which type of medical interfacing or like any kind of tests, any medical record, it can be fed directly to the AI engine or basically the model itself. So the model can like learn all these information and over time do kind of like predictive modeling in a lot of sense. Because for instance, with generative AI in machine learning or deep learning, we're trying to find what sort of pattern can we assimilate. So this is kind of like giving approximation. Now, in order to give that approximation, we need to train on huge amounts of data. So this is why I was saying that this depends on the amount of data or the amount of records that you basically want to include in, and based on that, the system can be fine-tuned, evaluated, and then pre-trained based on what type of technicality you need. So this goes into the personal prefix of how a person basically wants to design this, because this can also help the patient to provide further interaction directly, because like if you have already been to a certain doctor and you already have some, I guess, medical history prior, if when you go to another doctor and if he has access to all those information data, he can have a much more better sense of recommendation, fair judgment, and also the issue that you may be faced with. Now you might ask like, how can I deduce this thing in such a short formation? Okay, to give you much more clarity, think of it from this term. For instance, if you have any sort of itching issue, or maybe you're allergic to something, so there is a high possibility chance that if you eat or if you consume a certain element, it has higher priority that you will get sick. So this is the same way the brain or the model is tuned. So you can have experience as you move along, and with better information, and if you have previous history, it also helps the doctor to give you a much more better understanding of what type of kind of profiliation that he needs to give you. Because, for instance, if you have a medical history or record of consuming maybe pharmaceuticals, so if they are being intrigued to you in some sense, that information is stored in the database of the generative AI or the model. So the model can learn and distinguish and can give precision to the doctor. And immediately when your profile or your dashboard is viewed directly from the doctor's point of view, he can make a better judgment because all this information is available in the model itself. Now, I know that a lot of you might have the most prominent question of all, like, where does the security and privacy come in? So this is where the patient has the functionality within the user interface itself that if he wants, he can share his personal information, his record history, his management dashboard to all the previous information that he has. And the doctor can only view it when that patient gives that doctor that particular access. So here, the user or the patient is actually in charge of whether he or she wants to, share that personal information. Because, like, for instance, you can be like, okay, I don't want this data to be shared with this doctor, or if I don't want this information to be given to this doctor, you have that ability to choose. But please also bear in mind, the more information the doctor has, the better it is to accumulate and understand what type of problem you're actually facing. So, but at the end of the day, user comes first, so it depends on the patient if they want to share that information or not. And all this automation helps in a lot of context. For instance, if this is divided, let's say, into a subdominal part of, say, diagnostics, aftercare, therapy, screening, prevention, like all these records can be used for predictive modeling for a person. Because based on your patient history, your data, what type of health issues that you have, there is a possibility to train the model to see what type of future diseases that you might have. And this is where the AI diagnostic support comes into play because, like, for instance, if there's information about your MRI, if there's information about your X-rays, if there is intestine or any kind of management process involved, this is directly stored in the brain of the machine itself. So the AI can give you that perspective and that perception when it needs or to control your data because you have a unique ID in the system itself. So this is where this type of architecture has like its throughput of performance because this also relies very deeply on basically what type of machinery and what type of component you use. Because at the end of the day, this is based on how much data you basically want to include. For instance, let's say in a certain city or maybe in a certain region, if you have over 100 hospitals, you completely depend. Like I said, it's user oriented. So among those 100 hospitals, maybe 10 might say we don't want to share our data. So that's fine. So it depends on what type of data that you're basically going to use mainly. And based on that, based on the availability or the management system, you can include what you want in this particular architecture and this infrastructural automation of electronic health records. So this is where kind of it's a mixed method approach because it depends on how you utilize and where you basically utilize in a lot more sense to give you more better interpretation. So one of the key findings that we kind of find out that yes, it has its advantages and it also has some limitations because for instance, as I mentioned, the generative model can only perform at its peak or at its blooming performance if it has enough data. So in terms of response, in terms of like better management, reduced calibration, this is where the model will work at its optimal state. But at the same time, you also have the issue of synthetics, which is like prioritization of data, access to the data, limited amount of participants who are willing to like use their dashboard or provide that particular information because of course this is human systems biology. So a person can obviously say that I don't want this information to be shared. So security and privacy is also there, but at the same time, as I mentioned, this is both ways. If you want the left side to have like the throughput on the right, you need to give that information. It goes from the right to the left as well. So the main thing is the balance. And if you have enough amount of data and an amount of hospitals already intertwined, this can serve as a very big expansion, and like you don't need to make a necessarily other platforms. You can have one interpretable architecture, and that architecture can connect all the beams kind of like a node, and then you can like think of vertex and edges as like the connection between the hospitals, which ultimately goes to the main root of the tree, which is where the infrastructural architecture is there, and there the model is being trained so it can evolve, just like how our brain mainly functions in some sense to give you much more better clarity. So in terms of the experimental findings, I will not say that it is like at its optimal flow because, like as I've mentioned, depending on the clinical trials, the availability of the data sets, the availability of hospital records, this is where mainly the algorithm is at its finest. So depending on how much data you have, the better implementation that can be performed. So this was also kind of intrigued to make the user interface in this sense because like you don't need all the features. You can be like, okay, I need certain features and that's available. And depending on the severity or like how many type of management options or features you want to include, it can vary. So you have that ability to customize. And also at the same time, this is a much more lightweight model because like we didn't train it with like higher computational resource because first of all, we need that much amount of information. But in the sense that if developing countries decide to use this type of architecture, this prototype can be like a contribution for them and they can test, they can fine tune, they can learn using machine learning models, deep learning models, because the system is designed that way. So even if it's like with limited resources, the financial constraint and like the amount of utility or execution or development basically you want, that is where the fairness or I guess the multimodality is there. But in terms of responsiveness for healthcare delivery, for developing countries, this is like a pathway that they can move towards. So right now, the work is kind of like at a, I guess you could say in a stated state because like as evolving with ML models, DL models, there are a lot more blockchain technology coming in, which can be used as a very high-end performance peak for security and privacy. And because like this deals with human data, like biological data, so the mechanics and the learning algorithm can be fine-tuned better so that the handling is much more better because ultimately if this goes into automation, it would mean that the model itself needs to be trained very well and very precise. So like I said, it's from the data and the amount of, I guess, records that you basically want to put in. And so you might ask, like, why developing countries only? Well, the models that are currently being implemented in like first world countries, they already have kind of their mechanics. And because like, of course, they have the resources, they have the funding, they have all the I guess you could say features that they require, but for developing regions, there's still a lot more constraints. So from a scalable or like a lightweight foundation for intelligence healthcare systems, I would say this prototype serves basically as a strong, I guess, contender in a lot of sense. And with the improvement of generative AI, this can give much more better improvement in terms of operational efficiency, particularly for developing nations. And with that, I conclude my presentation. So if you have any questions, any queries, feel free to reach out. And that's it for my presentation. And thank you very much. Thank you very much for your attention.